In this video, I'm going to solve this optimization problem. So we want to build an aquarium that will be 6 feet high, and it's to have a volume of 750 cubic feet. The base, ends, and back are to be made of slate, but the front is to be made of plate glass, which costs 3/2 as much as slate per square foot. What dimensions should be chosen to make the cost of raw materials a minimum? So we'd like to minimize cost in this problem. So I'm going to label the lengths of the sides, y and x, and we are given that the volume is 750 cubic feet, so 6xy is 750, so y is equal to 750 over 6x, which is 125 over x. So in order to get the cost, I need to find the area of all of the sides. So the area of the back will be 6 times x. And the area of each of the sides is 6y. So the area of the two sides together is 2 times 6y, or 12y, which is 12 times 125 over x. I'm going to put everything in terms of x because I know I'm going to have to minimize cost, and I'd like to have it all in terms of one variable. So the area of the two sides is 12 times 125 over x, which is equal to 1500 over x. Now the area of the bottom is x times y, so that's x times y, which is equal to x times 125 over x, which is 125. Lastly, we have the area of the front, and materials cost a little bit more for the area of the front, and the area of the front is the same as the area of the back. The area of the front of the aquarium is 6x. So now let's go ahead and figure out a cost function. So let's let A be the cost of the back, sides, and bottom per square foot. Then we're given in the problem that the cost of the front, material for the front per square foot, will be 3/2 A. So then the cost is the cost of the back, sides, bottom per square foot multiplied by the area of those pieces, which we've already figured out, plus the cost of the front material per square foot multiplied by the area of the front, which was 6x. And A is just a constant. So the first thing I'm going to do is simplify this a bit and pull out the A. So in this first step here, I just factored the A out, and in this step here, I just collected like terms. Now I need to get the critical numbers, so I need to differentiate. And A is just a constant. So when I differentiate, the derivative I get will be equal to the constant A multiplied by the derivative of this piece. So there is the derivative. And to get the critical numbers, I need to figure out when C prime x is equal to 0. And remember again, A is just a constant, so C prime x will be 0 when this is equal to 0. So I should simplify that. So that is equal to 0. The derivative is equal to 0 when 15x squared minus 1500 over x squared is equal to 0, and that of course happens when the numerator is equal to 0. So the derivative is equal to 0 when 15x squared minus 1500 is 0, or when x squared is 100, and technically speaking that occurs when x is plus or minus 10, but we're talking about a length here, so the only critical number that matters in this problem is x equals 10. Now I need to prove that x equals 10 is going to give us a minimum. When I initially wrote out the function, I forgot to say that x needed to belong to a certain interval, so let's go back up and examine that. So here was c of x, and as you can see, x cannot be 0, and we're not on a closed interval here, so we won't be able to use the closed interval test, but let's write down x belongs to the interval 0 to infinity. So I have two choices. I can either use the first derivative test or the second derivative test, and I think I'll use the first derivative test in this example. So recall, this is our derivative here. This is our critical number, x equals 10, and I'm going to show that it gives us a minimum. So I'll go ahead and draw my sign diagram. And on this interval, the derivative is positive, and on this interval it's negative. So here it's decreasing, and here it's increasing. And this proves that, in fact, x equals 10 does give us a minimum by the first derivative test. I've written out my conclusion. By the first derivative test, x equals 10 gives a minimum, and I was asked to give the dimensions that minimize cost. The dimensions that minimize cost are 6 by 10 by 12.5 feet, and I got 12.5 because y was 125 over x, which is 12.5.